Hi there then, this is another look at hyperbolic functions. We're differentiating today, so let's have a look at some differentiation of hyperbolic functions. What do we get when we differentiate? I should really just tell you these. I know some of these proofs come up later on. So d dx, if I differentiate, it's a posh way of saying y equals cos x, therefore find dy by dx. So it's saying, what do you get if you differentiate cos? And the answer is sine. I want you to learn this. In a bit I'm going to prove it to you, but for now I want you to learn it. What do you get if you differentiate sine? Well, the answer is, rather nicely, cos. Now you may recall that when we differentiate sine and cos, you end up having to write, remember me doing this in the past, you have the signs change of sine and cos. Sine goes to cos, that's fine. Cos though goes to minus sine. Minus sine goes to minus cos. Minus cos goes to sine. So these, annoyingly, the sign changes each time. Plus, minus, whatever. But great thing about these is they don't. Sine becomes cos, cos becomes sine. Sorted. The next one I want you to do, or learn rather, is that tan. If we differentiate tan, we get sesh squared. So I think perhaps a reminder for you. I think I've done this, but just in case I haven't. If I do what are called reciprocal hyperbolic functions are, so sesh x is 1 over cos. That's where that comes from. So which implies there's probably a cosesh x, which is 1 over sine. And of course there is the third one, which is coth x, which is 1 over tan. They're directly analogous to the sec, cosec and cot, and they share a lot of the same properties. That's why they're given the names they are. They just happen to share a lot of the same properties. So this is one that we're meant to know. I'm going to prove that one to you a bit as well. And this last one, again, I might come back to that in a bit as well. You are meant to learn these four things. A brief word about differentiation. What we should already know, if I differentiate cos of 3x, the 3 comes to the front, but the cos doesn't stay. As I just said, sine, cos, minus sine, minus cos. I've got cos, it becomes a minus sine. So this becomes minus 3 sine 3x. I don't know why I wrote it there, because I know the answer is going to appear. The next one is sine 6x. So if I differentiate this, again, it should become 6 to the front. Sine becomes cos without any problem with signs, positive and stuff. So there you go, 6 cos 6x. Now, these three identities are something we've seen in normal maths. And if we haven't done, we will do more and more and more. So these three are very useful when you come, particularly for integration, when you need to integrate sine squared or cos squared or tan squared. These are the approaches you should use. So I'm expecting you to be able to do that. At the moment we're not integrating, so maybe we won't see that too much. Who knows? I can't remember what comes up in this PowerPoint. But we are expected to differentiate these things. Now interestingly, this says cos squared, and I could write it like that, but I don't need to, because cos squared allows me to use the chain rule. And the chain rule then allows me to bring the 2 to the front, 2 cos x. Now notice this becomes 2 cos x really to the power 1, because I lose a power in the chain rule. And the other thing I've got to then do is differentiate by the differential of cos. And cos becomes, as we see up here, cos becomes minus sine. So really I should put a minus in the front and then a sine x. Again, I wish I hadn't written it there now, because my answer will come up. There it is. It kind of does say minus 2 cos x sine x. The last one, which I'm going to remember now to give myself a bit of room, I get 4 moves to the front, so that's 4 3s are 12. And it says sine to the 4, so I lose a power, so sine to the 3. But then I have to differentiate the sine, and the sine becomes a cos. Sine becomes a cos. No plus or minus issues here. So that should be my answer, 12 sine cubed x cos x. So this is just how to use the chain rule, reminder really, because you know what's going to happen is it's going to come up in the hyperbolics. All right, and here's my proof then of that shine becomes cosh when I differentiate it. You will remember that shine is e to the x over 2 minus e to the minus x over 2. And the over 2 is kind of just a half of e to the x. And I should remember that if I differentiate e to the x's, it's still e to the x. So this is still a half e to the x. Slightly different for the e to the minus x. That minus with the chain rule means I've got to pull that to the front. And you can see that minus times by that minus will become a plus. So it's plus a half e to the minus x. And of course this is our definition of cosh x. I can do a very similar thing. I know it doesn't tell me to, but d dx of cosh. This is the proof. Again, that's the same as d dx. As I say, this is just a different way of writing dy by dx. So now cosh, of course, is exactly the same as this, but it's got a plus in the middle. So it's e to the x over 2 plus e to the minus x over 2. As I've just seen, if I differentiate e to the x over 2, the answer is e to the x over 2. Or, as I wrote there, half. The only difference is here it's got a minus, and so that minus comes down to the front on this one, and it's a plus at the moment, so it becomes a minus. You can see what's going to happen. This is shine x. So that's a proof that cosh becomes shine, and shine becomes cosh when I differentiate them. You should be aware a couple of things here. These used to be given to you in the formula book. That was the old formula book on the old modular paper that people did up until about a year ago. But now notice they have gone, and this is all you get given in your formula book now. So the OCR formula book is much more restricted in terms of that, and therefore you're meant to learn these. So you're going to have to learn these whether you like it or not. Of course, shine becomes cosh, cosh becomes shine isn't a problem. Than becomes sesh squared perhaps is. The great thing is though, look at that. Tan x, they do tell us, and it becomes sec squared. They always used to tell you this, but they used to also tell you that than becomes sesh. Now we're going to have to use this information, and this one actually, that's the same as the one I gave you at the start of the PowerPoint. Sesh becomes sesh than. That was a formula I gave you as well. So these can be extended, as can the others as well. Alright, now this is my proof then. So it says y equals than, show that dy by x is this. And of course this is another way. I just told you that cosh, 1 over cosh was sesh. So this is another way of writing sesh squared. So just be aware that that's effectively a standard proof. Now one way of thinking about this is if y equals than, then it is also equal to shine over cosh. That's a standard identity that we're meant to know. And therefore I can do this by saying dy by dx. Well, this is like my u is the top one, and I'm going to do the quotient rule on this. And my v is the cosh. And if this is true, u dash is, in fact I'm going to write up there, that's where I normally write it. Shine becomes cosh. And v dash, now I'm not sure if I've written u dash and v dash before. This of course is an alternative way of writing dv by dx. You might have seen that with some of the mechanics you've been doing. If not, it's fine. So quotient rule, I said, well the rule for quotient rule is v u dash, remember this is du by dx, minus u v dash, all divided by v squared. So what's my v is that times that initially, and that's cosh times cosh, which is cosh squared, minus uv dash, which is shine times shine, which is obviously shine squared, all over, it says v squared was v was cosh. And the great thing about cosh squared minus shine squared, again you should already know that sine squared plus cos squared equals 1. And the equivalent for hyperbolics is that cosh squared minus shine squared equals 1. So all this top bit becomes 1. This is cos squared. And that's what they wanted, and I can just finish it off by writing sesh squared as well. Okay. Another differentiation now. It says y equals x than x squared. All right. So this is a product rule. It's x times by that. So I'm going to write u equals x and v equals than of x squared. So therefore u dash du by dx is just 1. V dash, I suppose we need to just go back and just remind ourselves of what we've said at the start. Than is sesh squared when I differentiate it. So than becomes sesh squared. Now it says sesh of x squared. That's fine. But having done that, I now have to times by the differential of the bracket x squared, which is 2x. Now my rule for this is uv dash plus vu dash. So this becomes dy by dx is x times by this. So I reckon that's 2x times by the x is 2x squared sesh squared. And plus that times that, plus, well, let's just plus than of x squared. And of course, sesh squared means 1 over cos squared. Oh yeah, that should be x squared there as well. I nearly missed that because it was said there. And that's the same thing, so I'm happy with that. Your job then is to have a look at this. I mean, I'm guessing a lot of this will be fairly straightforward. Now we've done all those extra PowerPoints on some fairly basic and some quite difficult differentiation and integration questions. So have a look at this, see what you can do, and any problems let me know. Obviously this exercise will go on Moodle soon. All the best.